For centuries, humanity has chased the horizon, constantly seeking to transcend the limits of speed. From the first hesitant steps of powered flight to the breaking of the sound barrier, each milestone redefined what was possible. Yet, beyond the familiar roar of supersonic jets lies an entirely different domain, a frontier where the air itself becomes an adversary, and the very concept of flight is fundamentally challenged. This is the realm of hypersonic speed, Mach 5 and beyond. What exactly does hypersonic mean? In aviation, speeds are measured in Mach numbers, a ratio comparing an object's speed to the speed of sound. Supersonic flight begins at Mach 1, but truly hypersonic flight commences at Mach 5, 5 times the speed of sound. At sea level, this equates to roughly 3,800 miles per hour, or over 6,100 kilometers per hour. It's a speed so immense, it fundamentally alters how air behaves around a moving object. Reaching such speeds is not just about raw power, it's about confronting an invisible, yet formidable, barrier: extreme heat. As an aircraft hurtles through the atmosphere at Mach 5, the air molecules ahead of it are compressed and frictionally heated to astonishing temperatures. This isn't just surface warmth, it's an intense thermal assault, capable of degrading and destroying conventional aircraft materials in mere moments. The air itself becomes a furnace. Consider the temperatures involved. The leading edges and critical surfaces of a hypersonic vehicle can reach between 1,000 to 2,000 degrees Celsius. To put that in perspective, the melting point of steel is around 1,500 degrees Celsius, and aluminum, a common aerospace material, melts at about 660 degrees Celsius. Standard alloys used in commercial aircraft would simply liquefy under these conditions, turning a state-of-the-art jet into molten slag. This extreme thermal environment means that designing a hypersonic vehicle is not just an incremental step from supersonic flight, it's a leap into an entirely new paradigm of engineering. Every component, every surface, must be conceived with this brutal thermal challenge in mind. Traditional aerodynamic shapes and materials are simply inadequate. It demands a rethinking of propulsion, structure, and material science from the ground up. At the heart of sustained hypersonic flight lies an extraordinary engine concept, the supersonic combustion ramjet, or scramjet. Unlike conventional jet engines that use rotating compressor blades to squeeze incoming air, a scramjet has no moving parts. It relies entirely on the vehicle's immense forward speed to compress the air, a process known as ram compression. This elegant simplicity masks an incredible feat of engineering, operating at the very edge of physical possibility. To understand the scramjet, let's first consider its predecessor, the ramjet. A ramjet also uses ram compression, but crucially, it slows the incoming air to subsonic speeds before combustion. While efficient at Mach 2 to 4, this deceleration limits its top speed. The scramjet, however, takes this to the next level. It manages to burn fuel within a supersonic airflow. This seemingly impossible feat is what unlocks the potential for Mach 5 and beyond. Burning fuel in a flow moving faster than sound is akin to trying to light a match in a hurricane. The fuel and air are only in contact for milliseconds as they hurtle through the engine. Achieving stable combustion under these conditions requires incredible precision in fuel injection, mixing, and ignition. The flame must be held stable, preventing it from blowing out, even as the gases rush past at multiple times the speed of sound. This is the ultimate challenge for combustion engineers. A scramjet engine works by cleverly integrating the engine into the airframe itself. The vehicle's forward motion forces air into a carefully shaped inlet, or it's compressed by shockwaves without slowing to subsonic speeds. Fuel, often hydrogen or a specialized hydrocarbon like JP7, is then injected and ignited. The burning fuel expands rapidly, propelling the exhaust gases out a nozzle, generating immense thrust at hypersonic velocities. It's a continuous, supersonic chemical reaction. One of the most persistent challenges in scramjet development is flame holding. Imagine trying to keep a candle lit on a speeding bullet. The sheer velocity of the airflow naturally wants to extinguish the flame. Engineers employ various strategies, like strategically placed cavities or ramps within the combustor, to create localized recirculation zones. These zones act like tiny eddies, momentarily slowing the flow just enough for the fuel and air to mix and for the flame to stabilize and propagate upstream. The extreme temperatures generated by hypersonic flight pose not just a structural challenge, but an opportunity. One ingenious thermal protection strategy, known as active cooling, leverages the very fuel powering the engine. Before it's injected into the combustor, the fuel, often a specialized type like JP7 or cryogenic hydrogen, is circulated through passages embedded in the hottest parts of the vehicle's structure and engine. The fuel absorbs this intense heat, acting as a crucial heat sink. This heat absorption isn't just about cooling, it also preheats the fuel. For certain hydrocarbon fuels like JP7, this preheating can cause a controlled chemical reaction known as cracking, where larger molecules break down into smaller, more reactive ones. This process not only increases the fuel's energy content and improves combustion efficiency but also allows it to absorb even more heat, making the system a dual-purpose marvel of thermal management and propulsion enhancement. Alongside active cooling, passive thermal protection systems are vital. These materials are designed to directly withstand or dissipate the extreme heat. They don't actively circulate fluids but rely on their inherent material properties. This category includes advanced ceramics, carbon-carbon composites, and ablative layers, each engineered to perform under conditions that would instantly vaporize conventional alloys. Their development represents a cutting-edge field of material science. One key innovation in passive thermal protection is the ceramic matrix composite, or CMC. CMCs are a class of advanced materials made by embedding ceramic fibers within a ceramic matrix. This combination offers exceptional strength-to-weight ratios and, crucially, maintains its structural integrity at temperatures exceeding 1,650 degrees Celsius, far beyond the capabilities of even the most robust superalloys. They are lightweight, rigid, and incredibly resilient to thermal shock. Another critical passive defense is ablative materials. These are sacrificial layers designed to vaporize or char away when exposed to extreme heat, carrying thermal energy away from the underlying structure. As the outer layer of the ablative material heats up, it undergoes a phase change, sublimation or pyrolysis, absorbing vast amounts of heat in the process. This controlled erosion protects the core structure, similar to how a meteor's outer layer burns up during atmospheric entry. Thermal barrier coatings, or TBCs, provide another layer of protection. These are thin, ceramic-based coatings applied to the surfaces of high-temperature components. TBCs act as an insulating layer, reducing the heat transfer from the hot gas stream to the underlying metal structure. This allows the structural components to operate at lower temperatures, increasing their lifespan and reliability. They are crucial for both engine hot sections and vehicle leading edges. The challenge isn't just finding materials that can withstand the heat, but integrating them into a cohesive, functional airframe. This often means complex multi-layer designs, where different materials perform specific roles: an ablative outer layer, a CMC structural element underneath, and an active cooling system weaving through it all. The entire structure becomes a carefully orchestrated system of thermal defense and mechanical integrity, balancing weight, strength, and heat rejection. The shape of a hypersonic vehicle is not merely for aesthetics or lift, it's meticulously sculpted to manage the severe aerodynamic heating. Sharp leading edges generate more intense shockwaves and localized heating. Blunt shapes, while creating more drag, can distribute heat over a larger area, reducing peak temperatures. Engineers use computational fluid dynamics and advanced simulations to find the optimal balance, shaping the vehicle to minimize thermal load while maximizing efficiency. A classic example of such aerodynamic shaping is the waverider concept. A waverider is designed to literally ride its own shockwave, generating lift from the high-pressure air compressed beneath its unique, often wedge-shaped underside. This design minimizes drag and improves lift-to-drag ratio at hypersonic speeds, while also helping to manage the thermal environment by efficiently directing the superheated airflow away from critical surfaces. It's an elegant solution to complex problems. The journey to hypersonic flight is, in many ways, a testament to the relentless progress in materials science. It's about creating substances that defy conventional understanding, materials that can retain strength and structural integrity while glowing red-hot. From developing new ceramic formulations to engineering atomic-level structures that resist thermal degradation, every breakthrough in the lab brings us closer to mastering the extreme environments of Mach 5 and beyond. Developing these technologies requires extraordinary testing capabilities. Hypersonic wind tunnels, which simulate flight conditions at Mach 5+, are crucial. However, even these facilities have limitations, often running for only fractions of a second. Real-world flight tests are indispensable, pushing prototypes to their limits, gathering invaluable data on material performance, engine operation, and aerodynamic stability in authentic hypersonic environments. Each test flight is a dangerous, yet essential, step forward. The relentless pursuit of hypersonic flight is driven by more than just scientific curiosity, it's a strategic imperative. The military implications of vehicles capable of Mach 5+ are profound, signaling a fundamental shift in global defense and offense. The nation that masters this technology gains a decisive strategic advantage, capable of delivering strikes with unprecedented speed and, crucially, with unparalleled unpredictability. Two primary types of hypersonic weapons are under development: hypersonic glide vehicles, or HGVs, and hypersonic cruise missiles, HCMs. HGVs are launched by conventional ballistic missiles to high altitudes, then separate and glide back into the atmosphere at hypersonic speeds. Unlike traditional ballistic warheads, which follow predictable trajectories, HGVs can maneuver significantly during their atmospheric descent, making them exceptionally difficult to track and intercept. Hypersonic cruise missiles, or HCMs, are different. They are powered by scramjet engines for sustained hypersonic flight within the atmosphere. This allows them to maintain Mach 5+ speeds for extended periods and, crucially, to maneuver throughout their entire flight path. Unlike HGVs, which rely on initial launch altitude, HCMs are true powered flight at hypersonic speeds, offering even greater flexibility in mission profiles. For decades, missile defense systems have relied on the predictable, parabolic trajectories of intercontinental ballistic missiles. These weapons fly high into space and then re-enter the atmosphere along a well-defined path, giving radars and interceptors precious minutes to react. Hypersonic weapons shatter this predictability. Their ability to maneuver throughout their flight, combined with their extreme speed, fundamentally changes the calculus of missile defense. How do hypersonic missiles achieve this unparalleled maneuverability? They utilize several techniques. Atmospheric skipping involves them exiting and re-entering the denser atmosphere multiple times, extending range and confounding trajectory predictions. Low-altitude flight reduces radar detection ranges, and continuous in-flight course adjustments make any projected impact point a moving target. These combined factors create an almost impossible challenge for existing defense systems. Traditional missile defense radars are optimized to detect and track large, high-flying ballistic missile warheads from thousands of miles away. Hypersonic vehicles, however, fly lower, often within the upper atmosphere, and present a much smaller radar cross-section. The time available for detection, tracking, and interception is drastically reduced. By the time a hypersonic target is reliably detected, it may already be too close for any effective countermeasure. The speed of hypersonic weapons compresses the decision-making cycle to mere minutes, if not seconds. A conventional ballistic missile launch might offer 20 to 30 minutes of warning. A hypersonic weapon could potentially strike a target thousands of miles away in less than 15 minutes. This severely limits the time for human commanders to assess a threat, consult, and issue launch orders for counter-responses, escalating the risk of miscalculation. To counter the hypersonic threat, entirely new defense paradigms are being explored. This includes advanced space-based sensor layers for persistent tracking from orbit, AI-driven command and control systems for rapid response, and new types of interceptors designed to operate at hypersonic speeds themselves. The race is on to develop defenses that can match the speed and agility of these groundbreaking offensive weapons. The proliferation of hypersonic technology has profound global implications, potentially destabilizing existing power balances and accelerating a new arms race. Nations are investing heavily in research and development, understanding that mastery of hypersonic flight is not merely a technological achievement, but a geopolitical necessity. The strategic landscape is being redrawn by these advancements. Despite the remarkable progress, significant engineering challenges persist in the pursuit of routine hypersonic flight. Sustaining scramjet combustion over a wide range of Mach numbers, improving engine durability, developing even more resilient thermal protection, and integrating complex systems into a reliable, cost-effective platform all require continued innovation. The path to truly operational hypersonic travel is still long and arduous. While military applications currently dominate hypersonic research, the technology holds immense potential for civilian uses. Imagine flying from New York to Sydney in just a few hours, or launching satellites into orbit more efficiently. The advancements in materials, propulsion, and thermal management being pioneered for defense could eventually trickle down, revolutionizing commercial aviation and space access, transforming how we connect globally. The journey to Mach 5 and beyond is a testament to human ingenuity and perseverance. It's a story of engineers, scientists, and visionaries daring to confront what once seemed impossible, designing machines that can literally outrun their own heat, harnessing fire that burns faster than sound, and reshaping the very fabric of global strategy. Each challenge overcome pushes the boundaries of physics and engineering further. Every ounce of design, every material choice, every calculation is subjected to the ultimate test, the unforgiving environment of Earth's atmosphere at hypersonic speeds. The thin, superheated air acts as both a medium for flight and a relentless destructive force. Mastering this interaction requires a deep understanding of aerothermodynamics, a field that merges fluid dynamics, thermodynamics, and material science to predict and manage these extreme conditions. What began as theoretical concepts and complex equations in academic papers has slowly, painstakingly, transformed into tangible hardware. Experimental vehicles like the X-43 and X-51 Waverider have demonstrated sustained scramjet operation and hypersonic flight, validating decades of research. These groundbreaking test flights provide critical data, proving that what once existed only on paper can indeed soar through the sky at unimaginable speeds. The performance envelope of a scramjet engine is incredibly complex. It requires careful management of airflow, fuel-air ratio, and combustion stability across a wide range of altitudes and Mach numbers. From the initial acceleration phase, often requiring a rocket or turbine engine to reach scramjet ignition speed, to sustained hypersonic cruise, every stage demands precise control and optimization. The engine must seamlessly transition and adapt to changing conditions. The fuel system for a hypersonic vehicle is far more intricate than that of a conventional aircraft. It must deliver fuel at extremely high pressures and precise rates, often through actively cooled lines, into a combustor where it burns in milliseconds. Managing fuel density, temperature, and flow dynamics is critical, especially when the fuel itself is performing a dual role as a coolant. Every component must operate flawlessly under extreme stress. Igniting fuel in a supersonic airstream is inherently difficult. Unlike a conventional engine that might use a spark plug, scramjets often rely on pilot flames, catalytic surfaces, or even auto-ignition driven by the high temperatures and pressures of the compressed air. Ensuring reliable, rapid ignition and then stabilizing that flame against the overwhelming force of the airflow are critical hurdles that determine the engine's operational success. While hydrogen and JP7 have been the primary fuels for scramjet development due to their high energy density and cooling capabilities, research continues into other advanced propellants. Future hypersonic vehicles may utilize alternative hydrocarbon fuels, or even more exotic propellants, tailored to specific mission profiles or engine designs. The choice of fuel significantly impacts engine performance, thermal management strategies, and overall vehicle design. The design and optimization of hypersonic vehicles and scramjets heavily rely on advanced computational power. Computational fluid dynamics, or CFD, simulations allow engineers to model complex airflow patterns, shockwave interactions, and combustion processes in extreme detail, often before any physical prototype is built. This virtual testing drastically reduces development time and costs, enabling rapid iteration and refinement of designs that would be impossible with physical testing alone. Additive manufacturing, or 3D printing, is playing an increasingly vital role in creating the intricate components required for hypersonic flight. Complex cooling channels, lightweight structural elements with optimized geometries, and even entire scramjet combustors can be precisely fabricated layer by layer using high-temperature alloys and composites. This technology allows for designs that were previously impossible to manufacture, pushing the boundaries of what's physically achievable. Hypersonic wind tunnels are not just bigger versions of subsonic ones, they are specialized facilities, often using high-pressure gas reservoirs and expansion nozzles to create the necessary Mach numbers and temperature conditions. Many operate as blowdown tunnels, where gas is released from a high-pressure tank through the test section, allowing only short test durations. These precision tools are indispensable for gathering data on aerodynamics, heating, and material responses. For ablative materials, predicting and managing the ablation rate is crucial. Too fast, and the vehicle's structural integrity is compromised prematurely; too slow, and it won't shed enough heat. Engineers use sophisticated models and test data to understand how these materials char and vaporize under specific thermal loads. The goal is a controlled, predictable ablation that ensures the vehicle survives its fiery journey while remaining structurally sound. Heat flux, the rate of heat energy transfer per unit area, is incredibly high at hypersonic speeds, especially at leading edges and stagnation points. Designing for this involves minimizing these areas where possible, using active cooling, and applying the most robust passive materials. Managing this intense energy flow is a primary driver for the overall vehicle shape and material selection, ensuring that no single point becomes a catastrophic weak link. Beyond heating, hypersonic flight introduces unique aerodynamic stability challenges. The air at these speeds behaves differently, and the shockwaves generated can interact with control surfaces in complex, sometimes unpredictable ways. Maintaining stable flight and precise maneuverability requires sophisticated flight control systems, advanced sensors, and often, aerodynamic designs that are inherently stable at hypersonic velocities, a careful balance of form and function. At extreme hypersonic speeds, the air around the vehicle can become ionized, forming a superheated plasma sheath. This plasma can interfere with radio communication, creating a temporary blackout period for the vehicle. Mitigating this effect requires innovative antenna designs and communication protocols that can punch through or bypass the plasma layer. It's yet another layer of complexity that must be addressed for practical hypersonic operations. Hypersonic vehicles endure not only extreme heat but also rapid and dramatic thermal cycling, from ambient temperatures on the ground to thousands of degrees Celsius in flight, and then back again. This constant expansion and contraction puts immense stress on materials and joints, potentially leading to fatigue and structural failure over time. Designing for longevity and repeated use requires materials that can withstand these repeated, extreme thermal shocks without degradation. Beyond scramjets, researchers are exploring even more advanced propulsion concepts for speeds well beyond Mach 5. Combined cycle engines, which might integrate turbine, ramjet, and scramjet modes into a single system, could offer seamless acceleration from takeoff to orbit. Pulsed detonation engines and even nuclear propulsion are also theoretical possibilities, pushing the limits of speed and range further than ever imagined. The extremely precise operating conditions of a scramjet engine, and the tight tolerances required for thermal protection systems, necessitate precision manufacturing at every step. Even minute imperfections or misalignments can drastically impact performance, leading to uneven heating, unstable combustion, or reduced thrust. Robotics, advanced machining, and meticulous quality control are integral to building these cutting-edge machines. The engineering marvels of hypersonic flight are now central to a global race for strategic dominance. Major powers are heavily investing, not just in developing their own capabilities, but in understanding and countering those of rivals. This intense competition accelerates innovation, but also raises complex questions about international stability, arms control, and the potential for a new era of strategic uncertainty. As with any transformative military technology, hypersonic flight presents significant ethical considerations. The speed and unpredictability of these weapons reduce reaction times, increasing the risk of preemptive strikes or accidental escalation. Ensuring global stability in this new era will require careful diplomacy, transparency, and potentially new international agreements to manage the risks associated with such game-changing capabilities. Behind every technological leap are the dedicated individuals pushing the boundaries of what's possible. From theoretical physicists to material scientists, from combustion engineers to test pilots, thousands of brilliant minds contribute to the seemingly impossible feat of hypersonic flight. Their collective determination, intellect, and courage define this era of unparalleled innovation, transforming our understanding of physics and engineering. The technologies developed for hypersonic atmospheric flight also lay crucial groundwork for future space exploration. Scramjets could potentially power spaceplanes capable of taking off from conventional runways and accelerating to orbit, making space access more routine and affordable. The extreme thermal management and propulsion systems are directly applicable to spacecraft re-entry and high-speed planetary atmospheric entry, unlocking new frontiers beyond Earth. Beyond passengers, hypersonic technology could also revolutionize global cargo transport. Imagine delivering urgent medical supplies or high-value goods to any point on the planet within hours. This would redefine logistics, supply chains, and disaster response. The sheer speed offers unparalleled responsiveness, though the economic viability and environmental impact of such systems remain significant considerations for the future. Just as the sound barrier once seemed an insurmountable obstacle, the thermal barrier presented an even greater challenge. Yet, through relentless innovation in materials, propulsion, and aerodynamics, humanity is now systematically dismantling this barrier. The journey from subsonic to supersonic, and now to hypersonic, is a continuum of pushing against perceived limits, redefining the boundaries of what physics allows. The scramjet engine, a device with no moving parts yet capable of generating immense power at Mach 5+, stands as a triumph of fluid dynamics and combustion engineering. Its elegance lies in its simplicity of form, contradicted by the incredible complexity of its operation. It embodies the essence of hypersonic flight, harnessing extreme forces of nature for controlled, powerful motion, pushing the very definition of what an engine can be. While scramjets provide the thrust, the materials are the unsung heroes of hypersonic flight, bearing the brunt of the atmospheric inferno. Without the development of robust ceramic matrix composites, ablative coatings, and intelligent active cooling systems, the vision of Mach 5+ flight would remain firmly in the realm of science fiction. These advanced materials are foundational, a silent testament to human ingenuity. The advent of maneuverable hypersonic weapons has opened a new chapter in strategic warfare, effectively redrawing the global chessboard. Nations must now adapt their defense doctrines, invest in new technologies, and reconsider their alliances in light of these capabilities. The speed and unpredictability introduce a new dynamic, shifting the emphasis from brute force to rapid, precise, and elusive strikes, challenging existing notions of deterrence. The journey to Mach 5 and beyond is not merely about faster vehicles, it's a profound demonstration of humanity's capacity for innovation. It embodies the spirit of scientific inquiry, engineering excellence, and the courage to tackle problems of unprecedented scale. The lessons learned, the technologies developed, and the understanding gained will resonate far beyond the immediate applications, shaping our future in countless, unforeseen ways. The quest for ultimate speed continues. While Mach 5 represents a significant milestone, the human desire to go faster, further, and more efficiently is insatiable. Future generations of engineers and scientists will push beyond current boundaries, seeking even greater understanding and control over extreme physics. The era of hypersonic flight is not an endpoint, but a new beginning in humanity's endless pursuit of mastery over motion. As hypersonic technology matures, the international community faces the critical challenge of balancing its strategic implications with the imperative for global peace and stability. The dual-use nature of these advancements, offering both unprecedented defense capabilities and potentially devastating offensive power, demands thoughtful deliberation and cooperative solutions. The responsibility rests on us to guide this powerful technology towards a safer future. From the intricate blueprints of a scramjet engine to the shimmering plasma trails of a hypersonic glide vehicle, every aspect of this incredible technology represents a triumph over extreme conditions. It's a journey from theoretical limits to physical reality, a testament to what is achievable when human ambition meets scientific rigor. The sky, once thought boundless, now presents a new, fiery frontier to be conquered. The lessons learned from Mach 5 Plus flight are already inspiring the next generation of engineers and innovators. Students are delving into advanced fluid dynamics, pioneering new materials, and exploring novel propulsion concepts. The legacy of hypersonic development will not only be faster aircraft but also a richer understanding of fundamental physics and a renewed sense of possibility for what humanity can achieve. The development of scramjet technology has been a global scientific and engineering effort, with contributions from numerous nations, research institutions, and aerospace companies. This collaborative, yet competitive, environment has accelerated progress, pooling expertise and resources to overcome the monumental challenges. The shared pursuit of this high-speed frontier underscores the universal human drive to explore and innovate. Perhaps the most profound realization in hypersonic flight is that the airframe itself is an integral part of the engine. The entire vehicle becomes a seamless, integrated system where aerodynamics and propulsion are inextricably linked. The surfaces that generate lift and control are also shaping the airflow for combustion, a testament to the holistic design philosophy required to master these extreme speeds. Pushing the boundaries of physics comes with a significant cost, not just in financial investment, but in intellectual capital and the sheer difficulty of the task. Hypersonic programs are multi-decade endeavors, requiring sustained commitment, massive resources, and the acceptance of risk. Yet, the potential strategic advantages and revolutionary civilian applications are seen by many as a worthy return on this immense investment. From the first moments of acceleration to sustained cruise, and even during eventual deceleration, heat remains the constant adversary in hypersonic flight. Every solution, from active cooling to ablative shields, is a direct countermeasure against this omnipresent thermal force. The ability to manage and mitigate heat at such extreme levels is, fundamentally, the defining achievement of hypersonic engineering. The journey into hypersonic flight has opened a breathtaking new chapter in the history of aerospace. It's a realm where the impossible becomes tangible, where the very air we breathe transforms into both fuel and foe. The extreme engineering and physics behind Mach 5 and beyond are not just about raw speed, but about a deeper understanding of our universe and our own boundless capacity for innovation.